My dear students, today is the second day of our class. So, in this class I am going to first teach you about a new topic which is very important part of the lesson. Okay. So, write down the main topic, discovery of subatomic particles. Discovery of subatomic particles. Discovery of subatomic particles. Okay. Right. Under that topic, write down the subtopic. The subtopic is discovery of electron. Discovery of electrons. Okay, let's see the story. Story of the discovery of electrons. This is just like a story. It goes on, it's like a flow. Okay. So, last time I told you the scientist that named the word electron, who introduced the word electron, is the Stoney, but he doesn't know, he didn't know what is an electron, actually what are the properties of electron and so on. So the Stoney is just a scientist who named the word, but he didn't study properties of electrons and so on. Okay. So the discovery of electrons start with an experiment done by three scientists. So three scientists are, one is Crookes, his name is Crookes. Okay, that's the first scientist. Crookes, first scientist. And next one, there's a scientist called Pluker. Okay, Pluker. Then there was another scientist, Hitov. Okay. So there are three scientists that involved in the discovery of electrons. Okay, the initial experiment for the discovery of electron was done by these three scientists. The leader of this team is the Crookes. Okay, lead is the Crookes. Write down the note. Scientist. So write the names within inverted commas. You can write it in red pen or another pen. Crookes, comma, Pluker, and Hitov. Some like they are like some weird names, by the way. Okay, Crookes, Pluker, and Hitov. Okay, just stop writing. So what they did was this. Let's see. So the William Crookes, his name was, the full name was William Crookes. He invented a special tube, okay, a glassware, a tube known as Crookes tube. Okay, it was known as Crookes tube. This tube is a cylindrical shaped tube. It's like cylindrical, like this. And there are two electrodes where this was connected to external voltage supply, maybe to some high voltage supply. Okay. So then if we see, this is the negative terminal of the electric supply, this is the negative electrode. If this is the positive terminal, this is the positive electrode. As you know from last lesson, when we connect two electrodes to a battery, the positive terminal is the anode, negative one is the cathode. So this negative terminal is the cathode and this positive terminal electrode is the anode. Okay, what they try to do is they try to pass electricity through normal air. Okay, so they try to pass electricity through normal air. As we know, generally we cannot pass electricity through the normal air. Okay, the reason for this is, If we consider air, okay, if we consider air, there are gas particles. So lot of gas particles are there. So the air is made up of gas particles. Okay, it's like this. Okay, so if we want to pass electricity from this end to this end, so this is the in, this is the out. Let's see, there's a room, and there are two doors. This door is for to enter the room in, and this to exit from the room. Okay, now this room is fully occupied by lot of people. Lot of men and women are here and there, and they are highly crowded. Okay, there are no space between them actually. Okay, highly packed. So if we trying to pass any human being, any man or woman, from this door to the other door, it is very difficult for them to go through this room, because due to this high packing of people inside this room. Okay, like that, if we tries to pass electricity from one place to another through normal air, it is very difficult, because there are a lot of gas particles in air. Okay, like that way, these three scientists try to pass electricity through normal air. So it's a very difficult task. Okay, right. Now you try to understand this. So this was the experiment. These three scientists tried to pass electricity through normal air. Write down. Okay, we write these scientists' name. Hitov. So Crookes, Pluker, and Hitov tried to find out whether electricity would pass through gases, so normal air, through gases, but at normal pressure conditions, gases do not conduct electricity. At normal pressure conditions, gases do not conduct electricity. Okay, this is due to that reason I have already told you. Okay, right. Now write, this is the experiment that they did, and this used a tube known as Crookes tube. So what they did was this. Okay, so there are two electrodes at the opposite ends, and this glass tube is sealed one. Okay, then what they did was, they did two things. Okay, two things. Let's see here. If we want to pass this man from this end to other end through this room, we can do two things. Let's suggest two things to do. One thing is, we can open another door from the side of that room, another door, and we just let some of the people to exit out of this room. So we can evacuate the room by removing the people inside this room using another route or another area, another way, path. Okay, like that way, they did what they did was, as we know, when the people inside this room removes out of this room, so the crowd, the population, the crowd is, the amount of people inside become less. So the man can easily pass from this side to other side. So for this thing, what they did was, they connect this to a special apparatus, that is the vacuum pump. So this is connected to vacuum pump. Okay, to vacuum pump. You know what vacuum pump does no? So vacuum pump, what vacuum pump does is, vacuum pump removes the gas particles inside this tube. Okay, therefore the crowdness reduces, so the current can easily pass. That was one thing that we do to pass electricity. So we can connect this to a vacuum tube and we can remove some of the gas particles inside the tube. Okay. The next thing is we can use a very big man like Hulk. A very big man like Hulk, and tell him to just don't care about any people, you just go from this end to other end. So because he is very strong, he has high energy, he just crashes the people and people just go here and there like the Jim Papa in the Surappa series. So when the Roman carriers are there, just hit. So the Roman carriers throw in all the directions like that way. So we can, if we use a very high voltage, okay, like 10,000 volt between the cathode and the anode, so it's a very high energy supply, higher voltage. So due to this higher voltage, like Hulk, current can pass. Okay, write down. William Crookes invented a glass tube. William Crookes invented a glass tube sealed with 2 metal electrodes, at opposite ends. 2 metal electrodes at opposite ends. The air inside the tube was evacuated through a vacuum pump and a high voltage right within brackets like 10,000 volts, close the bracket, was applied to 2 electrodes. Okay, right. Now listen. Okay, then they did some other thing. Let's see, there are some other modification inside the tube. Listen, they placed a special screen or plate closer to the wall of the anode, and this plate or this screen was painted with a special compound known as zinc sulfide. This material shows a specific property which is known as the fluorescence. So this is the zinc sulfide fluorescent screen. So this zinc sulfide fluorescent screen was placed closer to the wall of the anode. What is meant by the fluorescent? Fluorescent means when there are some materials, when some of the radiation, so the rays collide or bombarded on those materials, they just glow. Like the signboards in streets, when we go through the streets, there are some signboards at night, they just glow with different colors, like that. When a radiation is collided with the fluorescent material, they just glow up, okay, like that. So, they glow with different colors. The zinc sulphide generally in here, this shows a pale green color glow. I will teach you that one later, just know this one for the moment. Okay. Then what happens is, just see, when the pressure inside the tube was reduced to 0.01 mercury millimeters, okay, when the pressure inside the tube was reduced to 0.01 mercury millimeters, that means this was done by evacuation using a vacuum pump. So, this vacuum pump evacuates the particles, gas particles inside the tube, therefore, the pressure reduces. As we know, when there are a high number of particles, there are a high pressure exerted between them. So, when there is less number of particles, when we remove most of the particles, the remaining particles can stay at some distance, so the pressure is low. As you know, when we travel by a bus at school time, there was lot of pressure because there are a lot of people inside the bus, but around 11 am or 10 am there are only few people are in the bus, so the pressure between them is very low, okay, like that. So, the pressure reduces to 0.01 mercury millimeters. At that moment, okay, at that moment they observed a specific observation. What is that? The area closer to around the cathode become darker. This area become darker, okay, darkuna, it become darker, like that. So, what they did was, they reduces this pressure further to 0.001. What happens was, then the whole tube get darker, the whole tube is now dark, like black, darker, and they observed there is a type of radiation originated from the cathode and travel towards the anode direction, okay. So, these rays, they are colorless, there was no color, colorless, no color, okay. It's like a sign, okay, glow around the cathode, then the radiations moves towards anode. When this radiation, these are rays, when these rays touches, when they collided, the fluorescent screen, this shows a pale green color glow, okay. A pale green color glow was observed. So, when they collide, observed pale green glow, there is a glow, okay. So, it was observed when these radiations, these rays touches, or when they collide the zinc sulphide fluorescent screen. So, the screen becomes a pale green color, okay. Write down, this is very important. They observed a glow, right, some sort of glow around here after the pressure was reduced to this amount, a glow around the cathode, a glow around the cathode, a glow around the cathode, which moved towards the direction of anode, which moved towards the direction of anode, when the pressure inside the tube, was reduced up to 0.001 mercury millimeters. 0.01 mercury millimeters. Okay. Right in the next line. These rays are what's the color? No color. Write down it and highlight the word colorless. Colorless. Highlight the word colorless. 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 And gave a green color glow. Gave a green color glow when it reached green color glow, pale green or green, that's okay, pale green or green, green color glow when it reached the walls of the tube, with a zinc sulfide fluorescent screen. With a zinc sulfide fluorescent screen. Screen එකක් හැටියට දාන්නත් පුළුවන්. Zinc sulfide fluorescent screen. Otherwise, if you can coat a layer of zinc sulfide on the glass wall, that is also fine. Either we can coat a layer of zinc sulfide inside the wall also, glass tube wall. Okay, that's also fine, or we can place a screen coated with zinc sulfide. Okay, now it's time. So you can draw this. Before that, I have to say one thing. So when they discovered a new ray, this is a new ray. It was at that time it was not found before them. So when we found a new thing, we have to name that. We should name that, no, right? When we found a new thing, we have to name that. So what they did was, as these radiations are originated, so they originated from the cathode and moves toward the anode. Okay, so these radiations originated from the cathode, so they named them as cathode rays. Cathode rays. Before drawing this, write this sentence also. Write down the below line. Since these rays are originated from cathode, they were called as cathode rays. Highlight the word cathode rays. They were called as cathode rays. Cathode rays. Okay, now draw the setup. This is the setup. Experiment done by Crookes, Fluker and the Hitov, 3 scientists. The leader was the Crookes. He invented the tube, Crookes tube, so I can label that one also. So this is the Crookes tube. After the discovery of cathode rays inside this tube also known as cathode ray tube, because the cathode rays were found inside this tube. Cathode ray tube. Cathode ray tube. Okay, draw the setup. Now draw the setup. Draw it clearly. I will give some time so you can draw. If you have any doubt, you can just WhatsApp me and you can ask any question at any time. Okay, I am always for your help. So as I told you, I am the one of the qualified teacher in Sri Lanka for the chemistry subject, because I am having a special degree in chemistry. So not like an engineering student or what undergraduate or any medicine students. I am highly qualified with the subject material. So you are joining the best class in Sri Lanka with the highest qualification from the highest university in Sri Lanka. So try to get the maximum advantage from me. So, you can ask any question and you can work hard and you can even get a very good rank also. So, okay. So, you have that trust, you can believe me because I have the whole potential in me and I can guide you in a way. So, you will easily do this journey, you can easily complete this one with some hard work and in a correct way. Okay, draw this. You can draw it neatly, okay, draw it neatly. Okay. So, after these three scientists did this experiment, okay, they didn't further study about the cathode rays. What are the cathode rays? What is the cathode ray? And the properties of the cathode ray? Those things are not studied by the Crookes and his gang. So, in those era, the main scientist right? The main scientist who was in the field is the J.J. Thomson. This is the main scientist. This is one of the main scientists in that era, J.J. Thomson. So what they did was, after this experiment, J.J. Thomson, okay, took this experiment, and he said that he will investigate the properties of cathode rays. So as they discovered the cathode rays, the scientists need to find what are the cathode rays and what is inside these cathode rays, what are the properties and so on. So in order to find the properties of cathode rays, J.J. Thomson did series of experiment, series of experiment by doing some modification to this setup, and he did some modification. I will teach you it in the next part. Okay. So Thomson did some modifications to this tube, and he found several properties of the cathode rays. Write down the topic: properties of cathode rays. Properties of cathode rays. Properties of cathode rays. Properties of cathode rays. Okay, write down the note. J.J. Thomson. So it's important, highlight the word scientist. He is the one who found properties of cathode rays. J.J. Thomson did several experiments. J.J. Thomson did several experiments. To identify properties of cathode rays. Several experiments to identify properties of cathode rays. Properties of cathode rays. Properties of cathode rays. Okay. Now I will teach you the experiments done by J.J. Thomson and the properties that he found regarding the cathode rays. Write down the first property, number 1. The property that he found first was, write down the first property, number 1. Cathode rays travels in straight lines. Cathode rays travels in straight lines. Okay. What he did was, so this is the modification. Let's see. So we no need to, when we draw, no need to draw these zinc sulfide one for each experiment. Okay. So this is the basic setup. So no need to draw everything, because they are all in all experiments. The basic setup is there, right? This voltage and everything is there. Okay. But no need to draw it always in all the, for all the properties. So no need to draw for each property. Okay. So I will simplify the setup. The setup is simplified just for your easiness. Okay. Otherwise the vacuum pump, the other voltage, they should be present at all the time. Okay. So then this is a tube. Let's say it's simple. Cathode and anode is there. So the voltage supply is also there. That's fine. Then cathode rays are there. Okay, what he did was, he placed a opaque object. Opaque means not transparent, non-transparent, a cross. Metal cross was placed in the path of cathode rays like this. A metal cross is placed like this. Okay, a metal cross was placed in the path of cathode rays. Okay. So what happened was, he observed when the cathode rays pass through this cross, he observed, okay, a image in the wall of the anode. So I cannot draw it here, because if I draw it in here, it's not clear now. So I will draw it here. This means this is in the wall. Okay. Just assume this is the wall of the anode, this wall. So I will draw it here so you can clearly identify. So he observed an image. So this is the object and there should be image. Okay. So image is observed and there is a shadow. This is a shadow. But the main thing is he observed this shadow with sharp edges. The edges of the shadow was very sharp. Okay, the edges are very sharp. Edges are very sharp. Okay, sharp edges. The edge is very sharp. You can see it clearly here. Okay, so it's not with a different color, but the edge is very sharp. Okay, so what he observed is, so this was actually observed in the wall of the anode. Okay, in here, if I draw it, it's not clear, no, so I draw it like in this position. Okay, so what he observed was a dark shadow. It's like a shadow, dark shadow, but with sharp edges. Edges are very sharp, with sharp edges. With sharp edges. This is very, very important. Okay, let's see. If we go to the sun at 12 at the 12 noon, at 12 p.m. What happens is we can see our shadow behind us. Heavenalla peenona ape pitipase heavenalla peenona. So if we see the shadow, the edges of our bodies is not sharp. It's like a blur. Blur which edges තමයි අපේ heavenalla පේන්නේ අවුවට ගියාම. හරිද? Edges were not sharp. The reason for that is when we are exposed to the sunlight travels, the solar radiations, also rays, they travels in all the direction. Here, this direction, this way, all around us, 360 angle degrees. So due to the traveling of the solar radiation, solar rays, sun rays in different directions, the edges are very blur. It's in blur nature, not sharp edges. So we cannot see our ear as a sharp edge on our shadow. Right? We cannot see our fingers as a sharp. These edges are not seen in the shadow of us. It's a blur one. Okay. So the reason is the sun, the solar energy, the solar radiations travels in different direction. Okay. In order to observe a sharp edge, that's an important thing, sharp edge. What happens is, let's see like this, if this radiation, this ray passes to the top part of the cross, if it travels in a straight line, it goes like this pathway, like this, and it touches here, touches the wall. Okay. So these points, this part is, you can observe it as a sharp edge. As they travel in like this direction, so a radiation passes through the bottom part, it just go in straight line and it collides the wall of the anode and it shows the same thing as the object. So the edge around the metal cross seems with sharp edges due to the movement of the cathode rays in straight lines. If the cathode rays moves in different directions, if not in a straight line, like this, if we see cathode rays moves in different direction, like this, it moves like this way, like that. So if that is the case, okay, we can just see some blur thing like this. The object is observed as a blur one, it's not a sharp edges, because if cathode rays travels in different directions, but as the cathode rays travel in a straight line path, the sharp edges were observed very sharper. Okay, that was the reason. So due to this observation, the sharp edges in the shadow, Thomson conclude that cathode rays should travel in straight line paths. Write down. Number 1, cathode rays travels in straight line. You have already wrote that one. Cathode rays travels in straight lines. Straight lines. Now write the note. When an opaque object, opaque means non-transparent, opaque object, non-transparent, okay, opaque object, like a metal cross, is placed in the path of cathode rays, is placed in the path of cathode rays. A shadow of the object, a shadow of the object, a shadow of the object with sharp edges, with sharp edges, with sharp edges was observed, with sharp edges was observed on the opposite side, on the opposite side near the anode, on the opposite side near the anode, near the anode. Because the shadow is with sharp edges, with sharp edges, for edges we can say it has margins also, sharp margin or edges, edges or margins. It confirmed that cathode rays travels in straight lines. It confirmed that cathode rays travels in straight lines. Cathode rays travels in straight lines. Straight lines. Okay. Now draw the setup. You can draw the cathode, anode, cathode rays, the metal cross, dark shadow with sharp edges. Draw it. Draw it neatly, okay. Draw the apparatus. So this was done by J.J. Thomson, and he found the first property of the cathode rays, which is the cathode rays travels in straight line path, okay, straight lines. Draw this and label the parts. As the New Year season is coming soon, so in the New Year week, most probably I know all of you are visiting your relative houses and you are enjoying the New Year festival, everything, most of you. So I think in that week most of the classes are also not conducting, no. So I will also give some vacation for that, because this month I am doing it for free, no. So any of you can watch this, please watch these videos, they are very important, okay, until the end of this month. It's very important, okay. You should watch all these videos, and you should write the note clearly. And in the WhatsApp group I am posting some polls and asking questions. You can answer those also. So, please answer those questions. So, they will update your memory and it will update your knowledge also. So, it's very important. So, we can do lot of works there. Okay, just participate in those quizzes and note those questions in polls. Okay, right. So, this was the first property that was found. Cathode rays travels in straight lines. So, let us see the second property that was found by Thomson. Write down the number 2. Write down number 2. Cathode rays have a momentum. You know the word momentum from your O levels, physics part. Momentum, mass times velocity, momentum. Okay, momentum. Right. Cathode rays have a momentum. You know the word momentum. Okay, momentum is equals to mass times velocity. Okay, this is the momentum, mv. Okay, mass times velocity. So, for rays, these rays, if they possess a mass, that means they should be particles, because particles has a mass. Okay. So, if Thomson can conclude cathode rays are having a momentum, that means there is a mass. So, if anything that has a mass are particle, that is a particle. Okay. So, there is a particle nature in cathode rays. Let us see how Thomson found this one. First of all, you wrote does the cathode rays have a momentum or a particle nature, Let us see what he did in this experiment. Particle nature. What he did was, just I will erase this thing, this. So, no dark shadow here. What he did was, he placed a paddle wheel in the path of cathode rays. A paddle wheel was placed. Okay, a paddle wheel means there is like something like paddles here connected to a wheel. The shape is like this. Okay. අර චූටි කාලේ අපි සෙල්ලම් කරා රූම් පැත්ත කෙලෙක්කින්. ඔහම අරගෙන ඔහම කරකෝන කැරකෙන පිබිනකොට කැරකෙන්නේ like that one. Okay, it's like it's called a paddle wheel. Okay, there's a wheel and there are some paddles connected to that wheel. Okay, so there's a paddle wheel was placed on the path of cathode rays. When these cathode rays collides on the paddle wheel, this rotates and this travels. It rotates and it travels like this. It travels. Okay. Room pettara අපි පිබිනකොට හොම මේව කරනකොට කැරකෙනවා වගේ, like it rotates. Okay. This also, when the cathode rays collides on the paddle wheel, it rotates. Write down. Okay. Should be a light paddle wheel. මොකද if we made this paddle wheel by iron, යකඩෙන් හදලා දැම්මොත් කරකවන්න තරම් energy එකක් cathode rays වලට නැහැ. Cathode ray doesn't possess a very high energy. It's very small energy, some sort of. So it cannot rotate a very heavier paddle wheel. Cannot rotate. So we have to use a light paddle wheel. Okay. Write down. A light freely moving. A light freely moving paddle wheel was placed in the path of cathode rays. was placed in the path of cathode rays. In the path of cathode rays, comma, paddle wheel is set in motion. Paddle wheel is set in motion. Set in motion slash rotates. Paddle wheel rotates. Simply paddle wheel rotates. Okay, it is set in motion. It was set in motion. Okay, set in motion or rotates. Showing that they possess momentum. They possess momentum. Okay, let's see ourselves. We have a mass, so we are made up of particles, mass. When we travel through a certain speed, we have the momentum mv. So if we have momentum, there's some plastic chair or something, some sort of, let's see, whatever chair or something is there, plastic chair. So when we move with some velocity and we collide with that chair, what happens? That chair moves this way. It goes like this way, because we are doing work, some sort of work, and giving some energy. That's a kinetic energy. We are using our kinetic energy because we have a momentum. When we have a momentum, we have the mass, we have the velocity, and we have the kinetic energy, half mv squared. Because we have the kinetic energy, we can do a work on object. So if there is a plastic chair on our path, when we are moving we are running at a high speed, if we collide with a plastic chair or table, it moves. Okay, so we can do a work on this object because we have the energy, or we have the ability to do the work due to the mass and the velocity. That means due to the momentum. So if we can do any work on an object, we can move that object. Okay, that means we can do a work. That means we have a momentum. So that's similar. So this, as the cathode rays are moving in a certain speed, velocity, as they collide on the paddle wheel, they make the paddle wheel to rotate. So they can, these cathode rays can do a work, as this example can do a work. That means they can exert, they can transform the energy. That means they have the kinetic energy because they have a velocity. So they have a momentum. So they have the mass. So they are particles. Write down. Okay, possess momentum. Write down the equation. Momentum equals mass times velocity. Write the equation. Sorry. Momentum equals mass times velocity. Okay, first, after that, after writing this equation, mass times velocity, draw the setup. Draw the setup. Draw the setup. Okay. Now write down. As cathode rays has a mass, as cathode rays has a mass, and can do a work, by rotating the paddle wheel, it confirms particle nature of cathode rays. Okay, that was the second property. The first one is the cathode rays travels in straight line. The second one is the cathode rays possesses a particle nature or a momentum. Okay, particle nature or a momentum. Okay, this is the first two properties. Okay, so then the next property which was found by the Thomson was, write down the number 3. Cathode ray particles. Now we can call them as particles because they have the particle nature. Okay, write down number 3. Cathode ray particles possess an electrical charge. Let's see how this was found by Thomson. Let's see how this property was found by Thomson. Okay. For in physics, in order to find whether a particle has any charge, okay, there's a simple experiment that we can do. Okay. So, in order to find whether a particle contains or possesses any charge, electrical charge, there is a simple experiment that we can do in physics, that is, we can place a magnetic field north pole and south pole. Okay. So, there is a magnetic field generated using two magnetic poles. Okay. Magnetic field can be generated using magnetic poles north pole and south pole. In between here we can see there is a magnetic field generated in this direction, okay, like this, from N to S. Okay. So, when a charged particles travels through, okay, a path perpendicular to the direction of the magnetic field, when they are perpendicular to each other, so the path of motion of the charged particle and the magnetic field, when they are perpendicular to each other, what happens? So, there is a force generated from the magnetic field on that particle, which is also in a perpendicular direction to the direction of the magnetic field. Okay. So, we know from the Fleming's left hand rule, that is the same thing. Okay. Okay. When there is a particle, the cathode rays are particles, as they travels like this, if any particle is having a charge, moves in a direction perpendicular to a magnetic field like this, there is a force generated in a perpendicular direction. So, due to the force generated in a perpendicular direction, okay, so they deflect perpendicular to the magnetic field. Okay. They deflect in a perpendicular direction like this. Okay. So, if this is the direction of the pathway, this is the direction of the motion of the cathode rays, if this is the direction of the magnetic field, there is a force generated on the cathode ray particles which is perpendicular to the direction of the magnetic field. Okay. So, due to this, they deflect perpendicular. We can write cathode rays deflecting perpendicular to the direction of the magnetic field, perpendicular to the direction of magnetic field. So it's given by Fleming's left hand rule in your O levels for physics part. Okay. So the deflection is perpendicular, so we cannot draw it in 3D, no, so we can draw it like this way. Okay, perpendicular direction. Okay, write down. So listen. So this happens only if the particles in the cathode rays possess any charge. Okay, right. Cathode rays are deflected. Write down. Cathode rays are deflected. Cathode rays are deflected perpendicular to the direction of the magnetic field. Perpendicular to the direction of the magnetic field. This shows that the cathode ray particles possess an electrical charge. So the number 3, the property, I think you have written the topic number 3. This one is the cathode ray particles possess an electrical charge. Cathode ray particles possess an electrical charge. That was the third property. Cathode ray particles possess an electrical charge. Okay. So this shows that the cathode ray particles possess an electrical charge. Okay. Draw the apparatus. Draw the setup. If there is no magnetic field, so if we remove the magnetic field, if we remove the magnetic poles, the cathode rays will move in the straight line pathway as normal. So this is the pathway in absence of magnetic field. Write it also. In absence of magnetic field. In absence of magnetic field, cathode ray particles travels in a straight line. But when there is a magnetic field in between that, in the perpendicular direction, so there is a force generated perpendicular to the direction of motion also, perpendicular to the direction of magnetic field also. So it travels in a perpendicular direction. So we are going to get some long vacation, a week, vacation more than a week. So it's just the beginning now for your A levels. So just don't try to do lot of things in these days. You just focus on what I taught you in these 2 videos. That's enough for these. So after the New Year season, we can begin the next parts. So no need to study a lot of things in this initial period. So you can just get the basic things first. Okay. Right. Now write down, as the cathode rays are, listen, before that listen. So in here, listen, these cathode rays, they are not attracted to these holes. north poles, for the north pole and for the south pole, the particles, cathode ray particles, they are not attracted. So, they move perpendicular direction. So, the magnetic field is in a direction which is perpendicular to the motion. Okay. So, they are perpendicular direction. Okay. So, if the cathode ray particles possess magnetic properties, we know when we closed a magnet to the iron bar or some iron materials, they get attracted because the iron has the magnetic properties. If any matter has any magnetic properties, they get attracted to the magnetic poles. Okay. But here the cathode ray particles are not attracted towards the north pole or south pole, they are deflected perpendicular direction. In a perpendicular direction. Okay. Not attracted to north poles and south poles. Okay. Write down, as the cathode rays are not attracted towards magnetic poles, cathode rays does not have magnetic properties. Cathode rays does not have magnetic properties. Cathode rays does not have magnetic properties. Okay. You have drawn this on, no? Already you have drawn this on, no? So setup is theirs. You should draw this. I think you have already drawn this. Okay, then I will wind up it for this is a short video. I am doing this, so I will try to do another video before the New Year celebration. I will try. Okay, I will try my best to do another short video. So I will explain the other properties. So as we know, there's an electrical charge in the cathode ray particles. Then there is a doubt whether the discharge is a positive or negative. So that was the idea, that was the thing that came into mind of Thomson after finding that the cathode ray particles possesses a electric charge. So the electric charge is two types, either it is positive or negative. So the next experiment was designed to find whether these cathode ray particles are positively charged or negatively charged. I will do another video this week. I will try my best to do another video. Then I will explain the other properties also, and I will finish the properties part in this week. So you have the vacation next week. Okay. So then we can start the next part after the New Year vacation. Okay, I will wind up here.